Hello everyone. So today I'll be talking about large scale training of LLMs and associated challenges. So this looks a bit weird because uh, it was not recorded on the day of the workshop because there was some audio issue. So I'm just recording everything so that everything is clear and you guys can actually understand stuff. So, my name is Suyog. I'm a part of BioAI lab, and I'm more on the programming side of the things rather than research side. I try to mimic, but I'm not uh, as proficient in research as I'm in programming. I think so. From all the things that you have learned so far in the workshop, you should be able to apply those after my session, and that's the key goal. And yeah, as the name suggests, you'll learn how to train these LLMs yourself and how you can actually go forward with this in any idea of yours, really. So, moving on, let's do a little introduction. The first thing you'll learn in this session is all the basics that you will need to know to get started with your own LLMs. Maybe you have a unique idea, maybe you have something that you would like to try out with the help of LLMs, or maybe you just have a really small hobby project that you think might use some LLM magic. We'll see how you can do all those things. We'll also touch on some of the most prevalent challenges currently, and we'll see some of the ways of mitigating these challenges that you typically encounter while you use LLMs. Um, and finally, there'll also be a programming demo at the end so that you can actually see all these things in action. And yeah, you'll know how to actually use the knowledge that you gained today. The library that we'll be using to facilitate all the LLM training that we'll do today is called Hugging Face, and it's a really good community. It's not a single library. It's a group of Python packages, and it's contributed by researchers, programmers all over the world. So it's stable, it's free and open source. So if there are any like small issues, they usually get fixed quite quickly. And yeah, it has become sort of this de facto standard in today's world after the advent of generative AI, LLMs specifically. So it has a lot of different models, pre-trained weights, and then data sets, lots of different tasks, and just a really good, easy to use interface that you can just quickly pick up. So we'll be looking into Hugging Face and all the different tasks you can achieve using Hugging Face. And then there is also a different library called Deep Speed that will actually allow you to train foundational models, not just pre-train or rather fine-tuned models, but also foundational models that require end-to-end complete training of a billion or more parameter model. We will see how it's being achieved today, because yeah, there are some challenges there as well. So we'll look into all of that. So let's first look at a usual LLM training workflow. And this really looks like any other deep learning tasks, any other deep learning tasks that you might have come across. But we'll just look at it from LLM perspective and see what are the small differences and where the challenges usually arise. So the first thing that you'll notice on the left over here is the training dataset. And one important thing to note about LLMs and their training datasets is that contrary to how you train any other deep learning model, you don't really uh, measure the size of your dataset in terms of number of examples, but rather in the number of tokens. So, for example, GPT-3, I believe, was trained on 300 billion tokens. What does that mean in practice? Is that the dataset that they used had 300 billion words. And this is a slightly better way of measuring it, because compared to other deep learning tasks, there is no clear label. In case of LLMs, it's simply predicting the next word, so you can actually use 300 billion words and then create different excerpts from it. Maybe you can prefix it with something and then uh, make it very specific to that task. So these are the different things that are possible. So that's why it's usually not measured in terms of number of examples, but rather in the terms of number of tokens. One token, it's simply put equivalent to a single word, but there are also some special tokens. There are like punctuation marks that are important. There are emojis. So it's sometimes more than a word, sometimes less than a word. And yeah, so a good rule of thumb is that a token is roughly equivalent to a word. So 300 billion tokens means that the text that they used, in total, it had 300 billion words, more or less. The next thing you will see on this flowchart is the inputs. That's the actual text. It gets through a tokenizer, and this tokenizer converts it into tokens, not embeddings. That's actually a mistake in the PPT. But these input tokens, they are essentially just like an index of that word, that emoji in a large token database. And these tokenizers also depend on the model that you're using. So for example, Google will use a particular tokenizer, but then Microsoft, Meta, they'll use some other tokenizer. And similarly, the outputs, which usually is also a text, it also passes through the same tokenizer and gets converted to similar tokens, again not embeddings. And then this is essentially the ground truth that we are trying to predict. And then this is where we will have a deeper look in this session. So this is your LLM. For the sake of simplicity, I've just represented it with a feed-forward neural network architecture, but it's obviously way more complicated than that. And then this is the hardware that we are using, which is typically GPUs, but it can also be NPUs, TPUs, can be CPU as well, although it will be slower. But there are some specialized processing units. And the LLM here, the way it's implemented in Hugging Face, at least, it takes care of actually embedding these tokens into vectors that you can actually use and compare with each other in n-dimensional space. So that thing is happening inside here as well. Just so you know, just so it's clear. And then it predicts some tokens again, and then these tokens are compared with ground truth tokens, and these two are compared with the loss function, which there are multiple of. And it says, okay, model good, model bad, whatever. It gives you a quantitative measure of how good the model is, and then you can use that to further tune your model. If that's clear, let's move on to the next slide. Challenges. So there are a few key challenges. Most of these I think are covered by other speakers in anyways, but I'll just briefly touch on them. When it comes to the data, which is arguably the most important part of any LLM training task today, so there are multiple concerns there. Uh, there are ethical concerns, namely, if you collect your data from a source, let's say you collect it from a public forum such as Reddit, Twitter, usually you need to make sure that the data that you're collecting does not have any personal stuff in it, because people post all kinds of things in there, and there's also names, there are addresses, there are yeah, there can be really private photos, and yeah, all these things you need to take care to censor properly, or at least get rid of the data that's not really necessary for the training of your model. And yeah, anonymize it as much as you can. So that's one thing that needs to be done. One good example that comes to mind is The case of GitHub Copilot. GitHub Copilot is a generative AI tool for programmers that helps them write good code. It's sort of an AI assisted autocomplete. Uh, and they what they did was they used GitHub, which has a lot of open source repositories, and they used that code to train their AI. And although they say that they looked at the licenses to make sure that the licenses were permissive enough, it creates a really unique problem where the licenses, or rather the person that put that license in their own repository, they didn't really know that in the future there'll be this unique problem with LLMs that can just generate code or generate any piece of text you want it to generate. So were those licenses created taking that into account? No one knows. And most probably those licenses didn't even have this specific term of deep learning model training in them. So that's sort of a gray area. But with all the new regulations coming in, this is becoming more and more clear by the day. Then there is also bias and prejudice against groups of individuals. This is also particularly true in the case of public forums where there are multiple people of multiple faiths, multiple beliefs, and you need to make sure that those don't propagate into your training methodology. Otherwise, your models will become too prejudiced. There are legal concerns. So, a good example for this one is the case of Dali. And Dali was trained on publicly available images created by lots of different artists from all across the world, and also some sites such as DeviantArt, and then there is Shutterstock, there is Unsplash, multiple sites. So there was a similar case there as well, similar to GitHub Copilot, where the artists, they didn't really want it to be used in that way, because the images that DALI or DALI 2 and then Midjourney or all these new stable diffusion models put out, those were uh, essentially copying the style of an artist's, of the involved artists. So that's not, that does not set a good precedent. And it's also debatable whether if you imitate someone's style, does that create a market alternative that harms the original creator. So obviously that's just from an ethical standpoint, but when it comes to a legal standpoint, uh, it can actually be a violation of their IP. So that's also a concern, and we need to make sure that consent is properly communicated. There's a proper waiver form that's filled out wherever necessary. Then there is environmental challenges, rising concerns that all these large scale LLM trainings, they are actually amounting to a large carbon footprint, which is largely true, because if you look at any past deep learning models, those were usually trained on a single 1080 Ti, and like not a lot of time was spent on it, maybe a week at most. But yeah, usually it was limited to a small cluster, a small workstation system, instead of a large data center of thousands of GPUs. So this does obviously lead to a large carbon footprint, and yeah, that's a concern to keep in mind. Hardware, and this is the most important concern that we will try to address in this session. So most LLMs, they are too large to fit in today's GPUs. And how do we overcome this memory limitation without sacrificing too much of the computational speed? So what I mean by that is the GPUs today, they don't really have that memory capacity. They were not really made keeping models of such scale in mind. So they are not tiny, but they are still not huge in terms of how much they can accommodate. So this is one of the key limitations of LLMs, and this is a really hot area of research right now. And obviously, if we try to compromise on memory, if we try to like fit more stuff in the GPUs, there will be some computational sacrifice, and we need to minimize that as well. So let's look at some of the let's look at this point in more detail so that it's a bit more clear. So NVIDIA A100, it's considered to be one of the largest GPUs on the market currently, and it actually has the highest amount of GPU memory of any GPUs right now, which is 80 gigabytes, which is a lot for most typical deep learning tasks, but not for LLMs. And this is a quote from NVIDIA's recent blog where they discussed all the new optimizations that they did in order to reduce the LLM training time. And it's so surreal to read because this would have been unimaginable just a couple years ago. So what they say is that training can now be done on a 175 billion parameter model on 300 billion tokens worth of training data using 1024 of these 80 gigabyte NVIDIA A100 GPUs. And they say in just, emphasis on just, 24 days, reducing time to results by 10 days or some 250,000 hours of GPU computing. So that's the scale we are dealing with in today's world. So 175 billion parameters, that's actually the size of GPT-3 model, and we need 1,000 of these high memory 80 gigabyte GPUs just to train them. So it's a bit wild. So whereas earlier you could have just used one GPU if you wanted, it would have taken longer, but you could have done that. You had that option. Now more than one of these GPUs is a requirement. So let's see what's the solution to this memory problem. And like most other things in computer science, the solution is parallelism. Uh, and we'll just look at multiple different modalities of parallelism that have been tried and are currently working really well. So the first one is data parallelism, and what it basically means is that you take the training data set and then split it into chunks and distribute the data to different GPUs. And the network itself, the entire training pipeline, that is also present on each of the GPUs. It's not split by any means. So as you can see in this diagram, this was the original pipeline that we had, and now it's replicated on all the available GPUs. So it's for a hypothetical 3 GPU system. So you can see the entire LLM model is replicated now on each of the GPUs. And then the training data set itself, it's been split into chunks, on into smaller chunks. So obviously this will reduce the training time as the data is now being split across multiple GPUs. And if model fits on a single GPU, and that's a big if in case of LLMs because most models will not fit on a single GPU. But if it does by some miracle, this is usually the fastest of all the options because this requires least amount of aggregation steps and least amount of modification or any sort of special stuff to be done. So this is the fastest option if your model does fit on a single GPU. And obviously this does not require any modifications to the model code because it's simply replicating everything on every single GPU. So it's completely, or rather mostly, stateless. So but if the model does not fit on a single GPU, this is completely infeasible. So that's one thing to keep in mind. So the next thing is pipeline parallelism, and it's also called vertical parallelism because we split the layers by a vertical slice here. And how it works is, suppose we had this sort of a LLM model with 3 hidden layers. We'll just basically put like a cut. I apologize for the bad drawing, but we'll just put a vertical cut and then split the layers, one or more layers on each GPU, depending on how many GPUs we have. And this does reduce the memory consumption of the model parameters on a single GPU. And if the model does not fit in a single GPU, this is still feasible now. But the thing to note here is that since you are separating these layers now, it requires modifications to be done to the model code. Now, the modifications aren't that heavy if they are just simple feed forward layers, but if they are attention layers, there are gradient pooling, uh, max pooling layers, and attention layers, for example. So, all these layers, they do not really work very well with this sort of model. So, you'll have to make heavy modifications, and eh, you know already that there are so many models available on the market. So when you are in that evaluation stage, where when you are trying to figure out what sort of a model architecture works best for your use case, this becomes very infeasible because it does not scale to all the models. You'll have to do different changes depending on the model. So that's one infeasibility for this sort of pipeline parallelism mechanism. And then the next one, which is a bit more adaptive, is tensor parallelism. It's also called horizontal parallelism because now we split the models by a horizontal slice, really. And this splits the computation such that the matrix multiplications that don't depend on each other are split in different GPUs. What that means, it's still very similar if you try to visualize it in layman's terms. It's very similar to basically just putting a horizontal cut through your model. But to be more precise, this is how it works. So usually you have an input, you multiply that with an with a weight matrix, and then the result of this multiplication is an output which might get fed into the next layer. So one way you can split this is by, so when you actually observe the values in this final matrix, you'll see that these multiplications don't really depend on these multiplications. So each of these rows can be computed separately from each other. So that's essentially what they do. So if this is a larger matrix, it's basically being split into smaller matrices now. And since they are independent operations, you can just split them on different GPUs, and then later you can have an aggregation step where they are concatenated back, and then you can proceed with your model computations. And if it's a fully convolutional model, I believe this can indeed be made in a way that reduces all these aggregation steps to essentially just like once or twice, and then that reduces queuing, GPU idling, all of that stuff. Uh, and about queuing, what I mean by that is that when you do this architecture, uh, so you're doing one pass, right? So an input arrives, goes through different GPUs, goes to the next layer, and then so on and so forth. Uh, it avoids GPU idling by essentially starting to process the next batch of inputs before the current batch of inputs has processed. So there's not a lot of GPU idling in this one, but this can become an issue in case of pipeline parallelism because in that the layers are just on different GPUs. So the entire computation has to move through all of the GPUs in a sequential manner, and their GPUs can stay idle if they are not scheduled properly. So yeah, this is pretty similar to pipeline parallelism as well in terms of its pros and cons. It does reduce memory consumption, but if it does require heavy modifications to the model code, so you can't really rely on it for testing a large array of models. And then the final one, and the one that we will spend the most time on, is deep speed zero. What the full form is zero redundancy optimizer, but it's a result of a recent research work from Microsoft, and this splits the computation in such a way that the model is split horizontally in each layer, and each of the GPUs then fetch the required values on demand from other GPUs. It sounds similar to tensor parallelism, but it's different. How is it different? Let's have a look. So in case of tensor parallelism, you had the parameters lying on different GPUs altogether, and then that GPU was only responsible for that part of calculation. But here, what happens is instead of that GPU only being responsible for that part, what it now will do is it will fetch all the values that it does not have from the rest of the GPUs and then do the entire computation itself. What this allows us to do is we can do data parallelism to some extent. So the all the GPUs, they are not processing the same data point. They are processing different sets of training examples, but they can still process everything and they save on memory because these values that are being fetched from other GPUs, they're stored in a buffer that's discarded as soon as it's used, as soon as it's of no use. It will be a bit more clear on the next slide. There is a video which will explain this in a slightly more detail. But since there is this buffer mechanism, it is slightly more, it consumes slightly more memory compared to tensor parallelism. But the larger benefit is that now each of the GPUs can do independent computations, which is really helpful. And it allows deep speed to combine uh, this approach with data parallelism and also a different thing called optimizer. That's also that's also getting optimized to work better. What I mean by that is the model weights themselves, turns out they are not the main source of all these computations, all this memory hogging on GPUs. Turns out the main source is usually the optimizer, because while you can uh, reduce the precision of your model weights to be 16-bit instead of 32-bit, thereby reducing its memory consumption by half straight away. You can't really do that with optimizers usually, because optimizers have to deal with large numbers. Even if they are not large, they have to deal with multiplications of multiple at least 16-bit weights, so they can get quite huge. So they usually, the optimizer calculations, they usually have to be done in 32 bits. And because it allows you to essentially sort of utilize data parallelization, or rather data parallelism, in combination with also splitting the model weights, it sort of hits that sweet spot between being fast enough and being memory efficient. So there are multiple pros to this. It reduces the memory consumption. It can fit on multiple GPUs even if the model does not fit on a single GPUs. And most importantly, it does not require any modifications to model code, which is really important because all of this can be handled entirely by DeepSpeed without any modifications required. And in addition to that, Microsoft DeepSpeed also implements a lot of other optimizations such as layer fusion, basically fusing multiple different commonly used layers to speed up the entire computation. And one more important thing is CPU and NVMe offloading, which essentially offloads some of the computation to CPU, or even just dumping them on SSD if you want to, like, utilize most amount of memory as much as you can. So if you have a billions of parameters model but you do not have enough memory on all the GPUs that you have, you can still train it, although it will be slower, by storing some of the parameters on SSD and then fetching them from there. And one commonly used thing here is CPU uploading for optimizer. So the optimizer, although it's calculating a lot, it does not require is it's not required to calculate the optimizer calculations on each training iteration, right? Because you can do mini batch optimization where you pass one training example, then the next one, then the next one, and after a certain number of training examples, then you do your back propagation. That's when you compute gradients and everything. So optimizer, if it's on CPU and its calculations happen after every a few training iterations, it will be slower than if you did that on GPU. But since it's not being done on every single iteration, it does still provide a good middle ground between using more amount of memory and using like being faster. So we'll see how it works with video. So it shows an example transformer model and a training dataset. It will be split on multiple GPUs, so you're still getting some data parallelization. And it says stage 3 at the top, but we'll explain what that means later on. First row, that block of memory is now assigned for parameters. The next row is for gradients. So gradients will basically store the back propagated gradients of any training iteration, and then the rest of the memory is being occupied for optimizer calculation. So you can already see how much memory you are actually saving by offloading the optimizer computation to CPU. Initially, GPU 0 that has the first row of weights, it will distribute that to everyone, and then everyone will do their forward pass, store the result of that computation locally. Similarly, the next GPU that has the next row of weights, it will send that to every single GPU. Everyone will do their work with that row, send it back, and then it goes on for all the layers. And as you can see, once the weights are sent, the computation is done. They are also automatically erased because you no longer need those weights, so you'll see them disappear. So you can keep reusing that same buffer, and so you essentially uh, need to consume only a constant amount of memory instead of having to store all the weights. So this is still saving a lot of memory. And then you'll see the backward pass starting, and again you'll require the different rows of weights, and those are now being fetched from different GPUs. Every single GPU does their calculation with that part, erases the buffer, and it goes on accordingly. And then if we skip further, you'll see it's just doing that same thing for all the layers and all the GPUs. Then once you have all the gradients, now you can uh, do your optimizer pass, or you can keep storing multiple gradients for multiple examples and then do one pass of optimizer at once for a bunch of training examples, basically mini batch gradient descent. And then as soon as the optimizer does its optimization step, the updated weights now get uh, used for the next iteration. Yeah, that's essentially how it works. One thing that we should probably know from this slide is the meaning of stage, what it means. So this is stage 3 in which the model parameters, the gradients, as well as the optimizer, all of them are completely partitioned across all the GPUs. In different stages, it's slightly less than that. So optimizer, in stage 1, it's just the optimizer that's being partitioned. In the next stage, it's the optimizer and then the gradients. In the next stage, it's optimizer, the gradients, and the model parameters. So there are different stages. And the next slide should just be for the demo. This is the QR code in case you want to access the code yourself and then run your own experiments. My camera will disappear. I will not run all of these slides because it takes a while. I'll just explain them quickly to you. So the first set of demos is regarding Hugging Face and how you can actually use it to create some really easy LLM tasks, really easy LLM models, and like just quickly spin them up. So the first thing you do is just go on Hugging Face's tasks web page, and then you can see all the different tasks here. You can just choose any one of these, and then you'll see multiple different models, multiple different data sets. So, and you can basically make a choice from there. This is an example tasks. If you click on it, it shows you what are the inputs, what are the outputs. It's just a sample, but that's usually how all the models will react. And then there's like tutorials. There is different recommended models, data sets. And there's also usually a demo as well. And let's see how we can load a dataset and do some sample tasks with it. So these are the imports that you usually do. Datasets, it's also a Hugging Face library. Transformers, it's also a Hugging Face library. This houses all the transformer based models. So there are also some image models that are in this library. And then to load a dataset, you just use this load dataset function. There are multiple versions. If there are multiple versions of that dataset, you can specify a particular one here. Once it's loaded, you can see the train, validation, test splits. So it's a really nice library. It has already done most of the work for you. So you don't really have to spend time creating your own split, then cross validation, whatever. It already has most of the things done for you. This is a sample of the dataset, and you can see it's a large piece of text, and then there is a summary afterwards. So this is a summarization sort of dataset. And let's see if we can get a similar summary by using a smaller LLM model, because larger ones take far too long to run. And to my knowledge, T5 small is the smallest model currently, which is still 60 million parameters, but that pales in comparison to billions of parameters in other larger LLM models. But this is what it looks like, and you'll see that this format is quite intuitive. So you just specify a task and then a model, and then these are some other parameters. You don't actually need to set them, but you can if you want to. And then they are, yeah, they just control how much of the output you actually see. Then you can choose to truncate the output, and there are multiple options essentially that you can go through the notebook and see for yourself. So this is a summarization task, and then this is a translation task. Let's see how they perform. If we go below, this is the original summary at the bottom, and this is the summary that's created by our T5 small model. And I think this summary that the T5 model generated, I think it's actually a much better representation of the text personally, but also it's not as succinct. And then there's also a summary translation to German that we are testing out. And yeah, I don't really speak German that much, so I don't know if this is accurate. But there was a German speaker in the audience when we did our workshop, and he he confirmed that some of these words, for example, this one, is apparently not German. It's probably something it's making up. So it's not perfect, but it's also a smaller model. So I think we can give it that. Anyway, zero shot classification. So zero shot classification, we've already seen what it means from other talks. Essentially, you don't really give the model uh, a lot of information, and it's asked to do a task that it's not originally been trained on. So you will see uh, a lot of different models on Hugging Face for this particular task, but the ones that I personally found to be working really well are these NLI models. NLI means natural language inference, and these tasks usually have a premise and a hypothesis, and then the model tries to come up with an explanation whether the premise is in any way related to the hypothesis. So, for example, if the premise is I have a cat, and then the hypothesis is I love dogs, there is not a lot of correlation between these two sentences, so the model will give it a lower score. But if I say I love cats, and then the second sentence is I need to get a cat, these probably have a much better correlation, so this will be closer to 1. And how you can use that in zero shot classification is by asking the model to classify a sentence into, let's say, multiple different labels, and these labels the model obviously has not seen before, or it doesn't really know what labeling even means. So I just gave it a sentence. This is a short demo session on zero shot text classification with Hugging Face conducted by Suyog. And then the candidate labels are computer science, sports, physics, biology, chemistry, mathematics. And then the way it's working in background is the model is being asked to compare two sentences. The first one of which is this sentence right here. And then the second one is going to be this sentence is about, and then this category. So this sentence is about computer science. This sentence is about sports. This sentence is about physics, and so on and so forth. And then the model will try to compare the likelihood of these two sentences being highly correlated, and that will be that's yeah, that's how it will rank the results, and then it will show you the output. So this is the output. The labels that it thinks this text belongs to are computer science with the highest probability, which is of 54%, and then mathematics, which does make sense because computer science, mathematics are the closest two things to any machine learning task. So it gives it the next highest score, but obviously it's not perfect. So apparently it's as related to mathematics as it is to sports. Maybe it got confused with the word shot. It might have thought that it means something related to a football kick or a cricket shot. Yeah. So it works fine for the most part. There is also a few shot classification in which you essentially give it multiple examples of the task that you wanted to do, and then yeah, it's slightly different from zero shot classification in that there is some context that the model has. And uh, let's see it through one example. So the example that we will look into is this text generation task from it's a model from Eleutheria. It's a large model, it's a billion parameter model. But what I want it to do is give me the object in a particular sentence. So if I say I am giving a demo to people, the answer should be people, and yeah, so on and so forth. So if you see without any context, it does a really terrible job. But if I give it some context, so the quick brown fox jumped over a lazy dog. The object is dog. Lazy dog jumped over the quick brown fox. The object is fox, and so on. And then if I ask it to do the same thing to I am giving a demo to people, let's see what it comes up with. And it says demo, which is not right. It should be people, but it works in some cases, it does not in some other cases. Yeah, so that's a sample few short classification task, and you might have better results if you just try the notebook yourself. No promises though. And there are also some references in case you want to learn more. uh, and then the next notebook that we will look at is about how you can actually train and scale your foundational LLM work, or you can just fine tune. You can also scale that. So we are testing this on a pretty good system with 8 NVIDIA GPUs, each of 40 gigabytes. We'll just quickly look at it. So the first import is the transformers input and then the data sets. And in the next cell, we load the dataset. This is Rotten Tomatoes sentiment classification dataset, and it has multiple excerpts of the reviews and then the sentiment behind it. So if it's a good review, then it will be a positive sentiment, and if it's a bad, it will be negative. You know what sentiment means. And this is a sample example, and then there are labels: one meaning positive, zero meaning negative. And this is what a typical model loading pipeline looks like in Hugging Face. You basically specify a particular model checkpoint, you load it using auto model for sequence to sequence LM, and then you basically just give it the name of that checkpoint. You also get the tokenizer by simply importing it. And then the next thing you do is essentially just map this dataset. This does not need to be done for all the datasets, but this pre-processing might vary. And this is the most important part then. And this is how easy it is to set up your training. You simply give it a checkpoint directory, a batch size, and then the name of an optimizer and how many epochs you want to train it for. And yes, that will give you a, a training arguments class that you need to use from transformers. And then you create a trainer from it, and it you give it the training dataset, which is simply the train split from the dataset that we loaded earlier, and then the evaluation dataset validation. Yeah, you start training, and this one takes around a minute, but since we are skipping this, we can directly see the results. Um, and you can see a sample memory consumption. In the beginning of the notebook, I restricted it to only use the GPUs 2 through 7. So you can see it's evenly distributing its load on these GPUs. That's the default behavior. And if we see the predictions that it has got, so the first review is, this movie is a waste of time, acting is terrible, ridiculous plot. Then this is supposed to be a negative one, this is supposed to be a positive one, in which it this movie is really good, great acting, so and so. And then the last one is just a nonsense review, movie good but bad. And this is a challenging example. So let's see what it says. And yeah, it says negative, positive, and then negative. So it apparently thinks that that's a bad review. But I have also had cases where it just spat out nonsense. So it would say good, bad, bad, good, or like positive, positive, negative, negative. So it's not your typical deep learning example where you just get the output 100% of the time. It is a very probabilistic sort of case, so you need to be aware of that. And let's quickly look at how deep speed can accelerate this. uh, so this is what you need to do in order to use deep speed, and this is the only part that you really need to worry about. You can specify if you want to offload the optimizer, which stage you want to use, if you want to use contiguous gradient so that there is not a lot of memory overload. And yeah, this is the entire config that you need to use. Yeah, I've also described the parameters which you can look into after this session is over. And the training is pretty similar to the earlier example, except that you also pass in this parameter where you say deep speed equals 0 config, and you pass in the configuration parameters. You can train it here as well, but right now at the moment of at the time of recording this session, it does not support training in a notebook. So we'll just use the command line, and when you use the command line, you have to specify how many GPUs you want to use, and then it will do the entire pre-processing pipeline, and it will just train the models, as you will see here. So it took around 27 seconds to train for 3 epochs, and it was a T5 base model, not the T5 small, which is 220 million parameters. So it took actually less time with the 128 batch size. But that's just a sample, and I don't have the NVIDIA SMI output right now, which I did have during the earlier session, but it will show you how each of the GPUs get pretty much the exact same amount. So I believe in this case it was around 28 gigabytes of VRAM being used on each of the GPUs. So yeah, you can run this notebook by yourself. There is also the environment instructions, everything you need to do on the GitHub repository that I have linked in the PPT. Yeah, and there are also references for you. So yeah, this is the QR code that you can use, and with that, I think yeah, that was all. Thank you for joining this session, and I hope you learned something new today. You can use the demo code from the link. It's licensed with a pretty permissible license, so you can just yeah, feel free. Thank you.